What's going on, guys? I am going to try to help you understand the problem deals with pressure at a certain depth of a fluid. The fluid in question is concrete. This whole thing is concrete. The specific gravity of concrete is 2.5 times the density of water. Now in this case we're going to use density of concrete will be 2.5 times 62.4. So let's find out what that is. I'm going to call this little p as rho. And that's going to equal 2.5 times 62.4. So that gives me 156. That's going to be feet cubed. So this problem, what they want to know is what the height is. It says a curved submerged surface in the shape of a quarter cylinder. The radius r at 1 foot is shown. The form can withstand a maximum vertical load of 350 pound force. So the radius is 1 foot. Can withstand a vertical force for V equals 350 pound force. Before it breaks, the width is 4 feet. So the width W is just 4 feet. Find the maximum depth, big H, to which the form may be filled. Let's worry about that. So let's establish some grounds, some boundaries. I'll call this my X and my Y axis. I will say that this is my starting point. Between here and here is my ending point, and I'll tell you why I need to determine the angle between them. As we have our pressure, and our pressure is just going to be rho g h. What is h? Since it's not, our origin is not at the surface, we're going to have to subtract this distance, and I'll call this middle distance right here d. So this plus this is going to give me the total distance. Call this distance little h. So I want to find this guy, big H. So big H is really equal to this little h minus d. Well, at this point, when h is the whole stretch is really the component of y, and really it's just what y would be in this direction. So our pressure is really rho g h, which is little h, which is r sine theta, minus d. Our force in the vertical component, we're also going to have our sine theta. Force is really the integral of the pressure times the area, because we want it in the vertical direction. There's a component in there's a sine component. Now what is our area? Our area will have to be found using a differential portion. So with respect to theta, our area would be anywhere between here to here, but I only really want it from the height h. So it'll be some point from here all the way to here, and of course this is the pi over 2s. So our area is going to be really the arc length. The arc length is just going to be r d theta times the width. So dA is r w d theta. We do need one more piece of information. Since we're starting from here, we're going to need to capture this angle. I'll call it some arbitrary name. I'll call it phi. So phi, sine of phi, well, the inverse sine of phi, well, not phi, but opposite of ridges will be d over r is equal to phi. So now I know where I can start. I can start from here, and I can end up at this angle. So I know this height. Other than that, I think we are pretty much done and ready to crunch some numbers.